So welcome to the IMPA seminar. Our speaker will be Marcelo Campos from IMPA, who will tell us about some amazing recent work on the singularity probability of random symmetric matrices. Thanks, Marcelo.
Thank you, Rob, and thanks to organizers for putting this together. So many amazing talks. And so today I'm going to talk about some joint work with Matthew Jenssen, Michelen and Julian Sahasrabudhe, where we proved that the singularity probability of a random symmetric matrix is exponentially small. And so first I want to start telling you about the case where B is a uniform random n by n matrix with entries in +1, -1, so not symmetric. And it's an old problem to actually determine what is the probability that the determinant of B is 0. And you can lower bound this probability by looking at the probability that either two rows or two columns are equal or opposite. And people conjecture that this lower bound is actually sharp, but it's very hard to show upper bounds on this problem. And all the improvements on upper bounds on this problem gave us excellent ideas, and that permeates the development of random matrix theory. So, for instance, Kamlash first proved that the probability that the determinant 0 actually goes to 0. He proved this n to minus a half, and it was only 30 years later that Kamlash similarity improved this to prove an exponential bound on this probability. This was further improved by Tao and Vu, who now gave a base for exponent of 3/4, and after that, Bruggen, Vu, and Wood improved it further, and until we got to Komarov, who finally got the correct base for the exponent in this probability. And he used some geometric framework that was developed by Rudolph and Versning, who gave an alternative proof of the exponential bound, but their proof also works to give least singular value. And this method that was developed by Komarov and Rudolph and Versning these ideas will be very useful in what I'm going to talk to you about today in this talk. And but this is not the end, right? Because the lower bound has some precise dependence, right? It was n squared here instead of this little n, and that is not known yet. And for optimal results, Litvak and Komarov showed the optimal result for sparse distributions, and James and Sawney showed the optimal result for non-uniform distributions. But it's still not known for this matrix B, right? But what we're interested in today is mainly the case where A is a n by n, it's uniform random n by n symmetric matrix with entries in +1, -1, and it is conjectured that the same bound, that the same type of behavior holds for the symmetric case, because you can also just pick the probability that two rows are equal or opposite to lower bound. But proving upper bounds is actually much harder, and only in 2006, Costello and Vu first proved that this probability actually goes to 0, and they proved this bound here. And this was further improved by Nguyen and Verschining, who proved super polynomial bounds independently, and Ferber-Jane proved this exponential minus constant n to the 1/4, and this was improved by myself, Matos, Morris, and Morrison to exponential minus constant root n. And finally, this was improved by log factors independently by James and Sawney, and by myself, Jensen, Michelen, and Sahasrabudhe. And you may notice that from last slide to here, we just improved by log factors, and seems like the improvement was sort of slowing down, but it's because there is a very natural barrier here at this point, at this exponential of minus constant root n log n, which you need to do something very different to actually overcome. And to talk to you about why that barrier is there, I'm going to tell you a bit about how these proofs usually work, which is generally we want to estimate the probability determinant 0. We just want to estimate the probability that there is some non-zero vector that the matrix maps to 0, right? And the general strategy in these papers is to union bound, or maybe you first approximate the vectors, then union bound. But the important thing is that you union bound over a bunch of vectors, and you only need to actually union bound over vectors such that this probability here, that the matrix maps it to 0, is large. And so there should be few vectors such that this probability is large. For most vectors, it should be small. And for the vectors such that this is small, Costello and Vu showed a decoupling lemma that actually deals with that. And so what is the strategy in these papers is, okay, so we are going to pick one row of this matrix. So let's look at the matrix A here. And let's look for one row of this matrix. What is the probability that this row in the product with the vector v is equal to 0? And if this is large, v should have some type of structure that allows us to count the choices for v and have few choices for it. And then when you union bound, the number of choices for v will be reasonably small, so the probability you get will win. But the problem is that when you actually want a union bound, you need to bound this probability here, right, for each of the vectors you're union bounding over. And to do that, what people did was usually to pick a set of independent rows, and that's why you wanna estimate you wanna deal with this quantity here. So people generally pick a set of rows here that are independent. So, for instance, if the rows are above the diagonal, right, and then they just use the randomness in this set of rows so that you can multiply just this quantity for each row. But they don't use the rows that are not independent. And so they lose a bunch of randomness. For instance, the randomness that is here above the diagonal. So it's like it's like we're assuming the worst case scenario here when we do this, like assuming this is 0, for instance. And this is bad because the below the diagonal things that are not independent should still be pseudo-random, so you should still be getting a bunch of information from them and that you are losing if you zero out. And it turns out that if you don't use this information below the diagonal, so if you don't use the rows that are not independent, if you just use a set of rows that is independent in this symmetric matrix, you lose, you are only able to prove this bound of exponential of minus constant root n log n, and that's also why the symmetric matrix problem is so hard. It's because you don't have the independence of the rows. And so what I want to tell you about today is this new result where finally we managed to get past this barrier of using the rows that are dependent on one another, and prove the first exponential bound on this probability here, the determinant is 0, for some constant here. And the constant is super, super small. It's something very, very, very small. It would be interesting. So it would be very interesting to actually improve this result, to prove like it with a decent constant here. Right. And so I wanna tell you a bit about the proof of this result today. I'm not going to be able to delve too much into details, but I want to give like a general picture of what we try to do and how we try to deal with this dependence of the rows of the matrix, which is the very hard part. Right. And so to start, let's we're going to do that strategy again of union bounding over vectors, but now we don't want to count all vectors by looking at just one row of the matrix and counting the vectors such that the probability that that row times the vector is 0. We want to look at the probability that count vectors with the whole matrix. And for this, it would be very useful to actually substitute the matrix A by this matrix M, where this like an absolute constant times n, and H is a matrix with IID entries, right? And we need actually to the entries of H need to not be only plus or minus 1, they must have some probability of being 0, just so the Fourier coefficients associated with this random variable behave well. But I think you don't lose too much by just thinking that the entries of H are just IID plus minus 1 random variables. And so we have H transpose here also. And so we need to use both the randomness of H and H transpose. And the main theorem we prove is given L, which would be a very large constant, and C here is an absolute constant that is just fixed. The number of vectors in the cube that satisfy that this probability here is large is a very small proportion of all the vectors in the cube. So how small this proportion is, so let's think, there's n to the n vectors in this cube, and we're having only a proportion of size constant to the n, L to the minus 2n of all the vectors in the cube. And so it's a exponentially small proportion of all the vectors in the cube that satisfy this. And just to give intuition why is, just to see why the scaling is like this, which might seem a bit confusing at first. So let's think, just to get intuition about the case where the rows of this matrix are independent, right? And in that case, you basically want, so this 2 norm being smaller than n is basically saying that you want each coordinate of this vector mv to be smaller than root n, basically. And this is for all n. So it's basically the probability of this and product over all n, right? And for each one, what is the probability of this? Well, it's like, it's basically, you're picking a matrix M here, and you're just picking one row and seeing what is the probability that it's smaller than root n. Sorry, there's an absolute value here, an absolute value. And so it's just a random walk. It's just the inner product of tau. If you think tau is just a thing, it's just the one row of the matrix M. The probability of this is smaller than root n. And now this is a random walk with n terms, and each entry of V has size big N. And so you should expect by the central limit term that this has like Gaussian behavior, and a Gaussian with standard deviation like big N root n, right? And so the probability that it's smaller than root n should be like 1 over n for a typical V. But of course, this is not true for all V, because, for instance, V could have some type of arithmetic structure, like all the VIs are equal, for instance. And in this case, this, instead of being 1 over big N, will be like 1 over root n and to the n, right? And big N might be much, much bigger than that. And so, but the interesting thing is that unless there is this arithmetic structure or this kind of weird structure for V, you should have basically this behavior, which is basically like this was a normal. And there's a concentration here. And what this is saying is that if you are L to the n bigger than the typical behavior, then there are very, very, very few choices for V. And this L to the minus 2 here might seem a bit strange, right? And so I'm going to explain why we want this L to minus 2, not like an L to minus 1 or anything else here, right? And so, okay. So why is this theorem useful for us? And now it will become clear why the L to minus 2 is here. Well, it's basically that when you want to bound the probability that the determinant is 0, remember that I said that we only needed to bound the probability that there is a non-zero vector, right? Such that the matrix maps it to 0. And I also said we only needed to deal with vectors such that that probability there was large. So that the probability that M of that AV 0 is large. So, and by large here, I mean exponential minus constant n squared, basically. Right. And to bound this, the idea is that we want to approximate each vector by a guy in one of these boxes. And we actually need to take more boxes. We can't just take this simple box. We need to like tile the space with lots of different boxes. But the important thing is that for all vectors, we're able to find, or for a dilate of all vectors, maybe I'll call it this U just so that we don't confuse it. Sorry. And AU equal to 0. And so for all vectors U, you should be able, and this is by a method called random rounding, which was introduced by Lifshitz in the context of random matrices and was used by Tikhomarov in his paper for the non-symmetric case. And by this method, you're basically able to find for each U a dilate such that you are able to approximate it by some V with the property that AV is small. So AV is smaller than N. And V is in this one of these boxes, and maybe you need more general boxes. And the final property that probability that such that AU equals 0 implies that AV is smaller than N, basically. And with the property also that if A is random, or let's now substitute by M, if M is random, then the probability that this is small is much bigger than what you would expect. And why should you be able to approximate U by this vector such that the probability is much bigger than what you would expect? It's basically because this probability that AU is 0 is much bigger than what is the normal behavior for you if this constant is very small. Because it should be for a typical U, this probability should be like exponential of minus a big constant times n squared, and here we're choosing a small constant times n squared. And basically, once you approximate this, where you're able to approximate all the U's by some vectors in these boxes, then you can just union bound over these boxes. And so it becomes clear that you don't need to union bound over all guys in these boxes, only for the guys in these boxes that satisfies this, right? And how many guys there are? There are this many. So it's this number. And for each one, we have the probability that it's smaller than n times the probability that MV smaller than n. And this is basically constant to the n, L to the minus 2n, n to the n. And this probability here will be like L over n to the n. And so now it becomes clear why we need this L to the minus 2n here, because the n to the n cancel with the n to the n. And then now, since we have this L to minus 2n, it kills the L to the n here, and we get a constant over L to the n here, which is exponentially small, and that's good for us. Okay, and so that's why we want to prove a theorem like this. And so how should we go about proving it? So the idea is that we want to use an idea introduced by Komarov, that you basically want to think of this, instead of thinking of counting, you want to now think that you are taking the vector at random from the box and estimate the probability that it satisfies this thing here. And so now you can think that each vi is independent and it's uniform in that in the interval n through 2n. And we now want to show this bound here, now this bound of constant L to the minus 2n on this probability. Right. And so how are we going to go about it? So let's remember what M was again. We had this matrix M, which was divided into those two matrices, H and H transpose, basically. And so if you look at M times V, it's basically, it's H transpose multiplying the last, and here's D, right? So it's multiplying the last D, n minus D coordinates of V. And for the first D coordinates, we multiply by H, right? And the good thing about dividing it like this is that these two random variables are independent in V, right? But they are not independent in H. So if you think of V as a random variable, these two random variables are independent. And we want to deal with each one separately now. And so let's first see what is the probability over H for this second one. And think about it for a bit. So what is the probability that this thing is close to 0? So the idea is that we can basically use the one-dimensional intuition now and just apply the methods that work for the IID case, because you can basically look now at this matrix H, and it has all independent rows. So if you just use what we call the inverse Littlewood-Offord theorem, for instance, the Rudolphson versioning method works here, you can show that for almost all choices of V, this bound here works with n minus D, since this matrix is n minus D by D, right? And it has all independent rows. And this for all but L to minus 2n proportion of V. Okay, and so this one is we can bound it by the methods that were already developed for the IID case, but what about the other random variable? And now the problem is that now it's conditioned, right? We want to now see what is the probability of this H transpose times VD plus 1 through n. This is small. And now it's conditioned on this thing here being small. So the big problem is that now we don't know how to deal with this distribution here, because the distribution of H is now conditioned on this constraint, and it's very hard to deal with that. And we are not able to actually figure out a way to deal with that directly. So, for instance, if you try Fourier analysis, the Fourier transforms don't work properly, and it's pretty, yeah. So we didn't find out a way to deal with that directly. So how are we going to deal with this event? Well, the idea is that now, instead of looking at the probability over V of that, of this probability being big, we are going to look at the expectation of this probability here, and basically apply Markov to this random variable here, right? So if you want to estimate this probability, you can just apply Markov, and so let's see what is the advantage of now dealing with expectations instead of probabilities here. So the interesting thing is that now you can write this probability over H as an expectation over H of an indicator function of this event here. And now you can swap the expectation over H with the expectation over V, and now have a probability over V instead of a probability over H of this event. So basically we need to deal with the probability over V of this event here, of H transpose times VD plus 1 to N more N. And now there is no more conditioning. Why is that? Because this random variable here, when viewed as a random variable over V instead of H, is now independent of this event here. And that's great for us. And just check, it's because the V, we are only taking in this event here the first D coordinates of V instead, and those are independent from the last N minus D coordinates of V. And so this event here is independent from this event over when viewed in the randomness of V. And why is that great for us? Well, because now the entries of V are independent random variables, and H is now a fixed matrix. So what should we think of this probability as being? Well, let's look at M again, just to get some idea. So if we look at this thing here, there are D guys here, and you can think that each row here of this matrix H transpose is giving one constraint on this vector Vd plus 1 through N here, right? And let's think about it being equal to 0 instead of just being small, just to get the right intuition. You don't lose too much by looking at it being equal to 0. So for each row, basically for each new linear constraint, you basically lose a choice of basically one coordinate of V, right? And so that gives a probability of 1 over big N for each coordinate of V you aren't allowed to choose. And so if there are basically, let's say D minus K rows here, which are independent, linearly independent, then we are putting D minus K different linear constraints on VD. And so this probability will be smaller than like 1 over N to the D minus K, basically. And so what that says is that if rank of, so what I mean by that is just that if rank of H transpose is basically D minus K, then you get 1 over N to the D minus K here. But the problem is that we don't know the rank of H transpose yet, right? And so the idea is that we want to also, and just to do a caveat here, we actually don't want to deal with, in the formal proof, we don't want to deal with rank because it's not just being equal to 0, it's just being small. And so we need a more robust notion of rank, so we use singular values. But here we can think of just rank, and it's enough to get the intuition of what's going on. And so what is happening is that, what is the probability, for instance, that the smaller the rank is, the bigger this probability here is, right? And so we actually want the rank of H to be as big as possible. But what is the probability that the rank of H is equal to D minus K, for instance? It should be like, so the intuition is that it should be like the probability that you have basically k rows that are equal, k plus 1 rows that are equal. Because that's what happens in the, because we have an IID random matrix, right? And a matrix of IID entries, and that's what people show that holds in the IID case. Is basically that, remember in the beginning of the talk, I said that the probability that the determinant 0 is, or that is, that if the rank is D minus 1, basically, is that the likeliest way is that 2 rows are equal. And now the likeliest way that the rank is D minus K is if K plus 1 rows are equal. And what is the probability of that? Is like exponential of minus, say, constant K, constant NK, right? And so this probability we get here should be compensating basically the minus K we're getting here from this, we are losing here, because N is like exponential of constant N. And so these two things should be balancing out. But the problem is, so going back now, so what we want to do is condition here on rank of H being like D minus K, right? And so we want to condition also here on, we want to estimate the probability that here, rank of H is D minus K. And we want to be getting, now, this type of inequality, we want to get some probability from this intersection here. And the problem is that these two events aren't independent, right? But we would like them to still behave as if they were independent. So we would still like to get an exponential of minus constant NK probability that we expect from this event here, still, even if those two events are independent. So we need to deal with this correlation between this constraint here and this constraint. And what we should think of this constraint that H is putting, of this constraint of rank as putting, is basically that it's putting basically K different linear constraints on H, and that we need to deal with besides this initial constraint that we already have of H times VD being small. And for each, and since the rows here of this matrix are independent, we're basically able to factor out, that probability into dealing with just the probability that each row of this matrix satisfies some linear constraints. And this is basically one of the main technical theorems we need to prove in the paper, and which is, we call a condition inverse Littlewood-Offord theorem. And the idea is that there is an absolute constant C such that if this large integer, and alpha is small, we can choose choose it to be a small constant, and K is linear in D, and big N is allowed to be exponential in D. So big N should be you should think of it as the same as in the last slides. All the constants, everything that is appearing here, the K and the D, you should think of it as being the same as was appearing in this last slide. And in this case, if you pick W representing the linear constraints that are constraining our rank to be D minus K, and tau to be the one row of that matrix H, so it's a random vector, uniformly random from +1 to -1 to D, then the following inequality holds, which is basically what we want, which is holds for almost all choices of vectors, which is the type of condition we want also in the last theorem, where we want to choose probably alpha to be something like L to the minus a large constant, and that's where the restriction on N comes from, on the size of the exponential here, on the size that n can be, and to have a very few choices of v that satisfy this inequality here, which I'm going to explain in a bit. But just to check, this is telling us about the behavior of one row of the matrix H, right? Which was n by n minus d by d. And so since the rows of this matrix are basically independent, this thing here, the behavior in the final bound, we should get this side and this side to the n minus d, basically, right? We should have this to the n minus d and this thing to the n minus d, which is exactly the behavior we wanted to prove, the bound on the probability that we wanted to prove. But so, and now just to explain why do we want why this bound here is the right thing. So first, this constraint here comes from this constraint here, from this event here. And why should we expect this probability to be like this? Basically because if we look at each row of this W, so there are d rows, there are k rows, each of size d, we are looking at this probability here is basically the probability that this holds for every row of this matrix W. And what is the probability of that? This is like, this should be like exponential of minus constant, because each Wi is a unit length vector. So the standard deviation of this random variable here should be like 1, and it should have normal like behavior. I think you can, yeah, this is actually true for all Wi of unit length. And for the other part, and so when you multiply this for all the k rows, and they should be roughly independent, you should think, because the rows are orthogonal to each other. So they should behave, so these random variables should behave roughly independently. And you can actually show a version of this result here by just using Talleyrand's inequality, but you don't get the right constant, I think, by using Talleyrand. And then there's the other constraint which is for v, and of course this doesn't hold for all v, because again v can have some type of arithmetic structure that that doesn't allow this thing to be true. For instance, if all the vi's are equal, or if they are in a very short interval here inside. But in general, for a typical v, you should hope that this is true, because of the same reason, that the vi's are size like n, big N, and so this thing has standard deviation like n root d, roughly. And so the probability that it's smaller than constant root d should be like 1 over n, big N. And so this can be shown formally for that. So if you just ignore this constraint here, you take, for instance, k to be 0, this theorem is still hard to show, and it was shown by Rudolph and Verschning, and without k. And so that very hard thing is to actually get both constraints at the same time. So you have these two events that you know how to bound by previous works, this by Talleyrand, this by Rudolph and Verschning, but showing that they actually decouple somehow, that the probability that both of them happen at the same time is smaller than what you would expect if they were independent, is the very hard part. And I think I still have a bit of time, so I can tell you just give a hint of how we prove this theorem. And so the idea basically is that we want to count the number of vectors that don't satisfy this condition, these two that don't satisfy this condition here. So such that this inequality here works, this probability is bigger than this. And the idea is that we are able to find some real number phi such that the distance of at least half the coordinates to this arithmetic progression is smaller, much smaller than what you would expect. So let me just do a drawing here. So if you just look at this thing here. So basically, so this should be phi z, and the places where we can choose the VIs are like this, right? And so only alpha proportion of the root alpha proportion of the choices for VI will land on the one of these red intervals, right? Of this red AP. And since this holds for d/2 coordinates, and each VI is, you can think of it as choosing each VI independently, you get a root alpha to the d/2. So you get the bound that we wanted there. That proportion of VIs that that actually don't satisfy this condition. And to actually prove it, we do it by what you usually do is you find this phi by taking a Fourier transform and looking at level sets. And then when you start looking at the level sets, this becomes very, very related to what's happening. And that's what actually roots and versioning do. And they take a Fourier transform, but without this event. And the advantage of rootless inversioning is that in their case, when they take the Fourier transform, the level sets is one-dimensional. So you need to do some geometry to actually find this phi, but you're able to do it in one dimension. And our problem is that when you take the Fourier transform of this, you end up needing to deal with k+1 dimensional sets, where k can be very large. And so we need to do some much more complicated geometry there, because we aren't allowed to choose to just change measures freely. And because in high dimension, we need to be very careful with what we are doing, since the dimension is very high. And I think that's it. Thank you so much.
Let's thank Marcelo for a great talk. Are there any questions? Please jump in.
You can have good questions.
Yeah, please go ahead.
Yeah, right. So first, congratulations on the very nice result. So how flexible is the result? And of course, it's very technical. And so how flexible? Because you mentioned at some point that you have some inequalities. So it would also give you some quantitative version on the singular value.
Yeah, I think so. Yeah, it's I think the method works in the same way for least singular value. The only problem is only more technical, right? It's just, and then we wanted to write the cleanest paper, so we stuck with the singularity. But I think the methods work in the same way, because since it's the rootless inversioning framework, it all fits in the same way.
Right, because so in versioning papers, it has two parts, right? One part is for the continuous part, which is like you have epsilon to the power if you want to see how far away from zero. And the other part is the discrete part, which is exponential that you mentioned. So now you improve the discrete part. And I guess that that is also improve the continuous part.
Yeah, I think so. Yeah.
Oh, that would be great. And then to the optimal epsilon. It's not like, I think we're sharing.
No, I think we don't get the optimal epsilon. We get the epsilon to the 1/8, right? The problem is that the decoupling, I think in the singular value, the decoupling lose a 1/8 factor in the epsilon. So you get the probability. It's at most epsilon to the 1/8, and so it's very interesting to actually try to remove that 1/8 from the exponent.
So you guys are not able to remove that just yet?
No. Yeah, we are. Yeah.
Another question is also, I think at some point you have to, like, you forget the diagonal blocks and you ignore it to be 0, but I guess that have some effect in your bound that you get smaller than truth error or something like that. Is that so? Is your result extend to the perceived version when you perceive the matrices a little bit?
Sorry, say it again.
For example, I think here you have like you have a matrix, determinist matrix, and you perceive it by this random, and then you look at the singular value, the singularity problem. Does it extend to that case?
Yeah, that's a good question. I don't know actually.
Because I saw in the bound that you get involving the H and the HT, you bound it from the norm that is bounded by root n or something like that. Again, yeah, you implicitly using that the norm of the blocks is bounded by root n, I guess.
Yeah, but I don't know if the replacement would work. Like if you do, can't you do replacement in the case that the random variable is non-centered? I'm not sure if that would work or not.
Yeah, that would be great to check.
Yeah, that's yeah.
Right. So thanks.
Thanks.
Thanks, Ray. Any more questions? No? Well, if not, I guess it's already 10 to, so we can thank Marcelo again for an excellent talk.